Forbes, and to make things really clear, I'm not a physicist. Most of what's been said over this past few weeks has been about 50,000 meters over my head. I'm not an engineer. Okay? I'm an economist. And yet I think I have something to offer because I believe that, given the state of the economy, that's saying a lot, given that I think there's very, very large gains to be made from an interdisciplinary approach to space weather. Okay. We all know that space weather can lead to, Hydro-Quebec type blackouts. But what about the rest of the time? Okay. So the title of this talk is Establishing the Economic Impacts of Space Weather, the Case of Electricity. And I first wanted to acknowledge the contributions of my co-author, Chris St. Cyr, who many years ago sent me this email entitled, Question Out of the Blue. Do you know anything about space weather? So, I also want to acknowledge that this research is supported by NSF. And so let's get going. Okay, organization of this talk. First, I'm going to start off talking about electricity markets. Oh, of the students here, this is not, first off, the good news is there will not be a pop quiz. There's no homework, okay? But how many of you have had a course in economics? That's great, that's great, that's great. Okay, and as we go through the talk, half of what I'm going to say will be totally alien to you. Unfortunately, I just don't know which half. And so if I'm going over something that's the least bit unclear, this is the time to ask. There's also a draft manuscript on the website that goes into, I think, a little more detail if you want to know more. Okay. This particular talk focuses on the PJM power grid in Northeast United States, but my research with St. Cyr also talks about other power systems, including the UK and a lot of systems in Europe. Okay, organization. First, we're going to start off talking about electricity markets, which is a very recent phenomenon. We're then going to be talking about GICs and prices in what's called the PJM Regional Transmission Organization. It's a very large electricity control area in the Northeast. And what we're going to show here is that there's a statistical relationship between the GICs and what's called the real-time price of electricity relative to the day-ahead price. And part 3, we're going to ask the question, so why does this happen? Why are the prices, the real-time prices, why are they affected by geomagnetic activity? And then the 4th section is, what can we do about this? Okay. Or is this just simply an exercise that's interesting but has no practical relevance? Okay, background. A substantial portion of electricity generation in the United States and throughout the world is now coordinated by electricity markets. So if you go to Europe, for instance, the coordination of generation in France takes place through an electricity market. Same in the UK. Same in Scandinavia, same in Germany, okay. Same in Australia, same in New Zealand. So we now have, for the first time over the past 20 years, we've seen this movement to using markets to coordinate generation. These markets in the United States are operated by organizations that are known as regional transmission organizations, RTOs, or ISOs, independent system operators, they're the same thing. In many cases, these organizations operate two markets. There's a day-ahead market where market participants can buy power or sell power for tomorrow, but you lock in the price today. That's a day-ahead market. In finance, we would call this a forward market. And then there's these, what also happens is these organizations tend to operate what are called a real-time market, where the prices depend upon real-time operating conditions. Okay, and here's a map. Here's the Electricity Reliability Council of Texas. They actually have a market for electricity. Alberta has a market. California has a market. Midwest ISO. Ontario has a market for electricity. New England, New York, and then this blue is the current geographic footprint for PJM. What is really striking to me as an economist, but perhaps not to you, is that if you look just in the United States, most of these markets occur in what are called blue states, with the exception of Texas. So for instance, the southeast here, there's no electricity market. These are all red states. Okay, I thought it was interesting. Okay. Okay. My apologies. The red states tend to be, these are states that are these, how can I put this politely? These are the really right-wing Republican states, okay? I think that was polite. And then the blue states tend to be more democratic states. And so here in the all throughout the Northeast, those are largely democratic states, and yet, the Democrats tend to be a little skittish sometimes on using markets. Okay. Some people would say those Democrats are socialists, in fact. But yet, these were the first states, as well as California, to use markets to coordinate generation. Okay, so the outcomes in these markets are increasingly being recognized as being informationally efficient. Now, if I can put in an advertisement, I will. And the advertisement is one of my co-authors and I, we've recently filed a patent application to tap into this informational efficiency in these markets to produce better load forecasts. Load forecast being a forecast of electricity consumption. Okay. This informational efficiency is believed to occur because the generators are dispatched based on an auction in which the market outcomes reveal the expected operating conditions. So you have an auction, and the results of the auctions have information. And we're going to use that here today to help reveal space weather impacts. And the reason, what happens in these markets is you have scheduled dispatch of generation is based on the day-ahead market for electricity, which is based on offers to provide generation, which in turn is based on what economists call marginal cost. Okay. The offers are generally accepted beginning with the lowest price offers. So the people who can produce the electricity the cheapest, they'll bid into the market very, very low prices because they want to get their generators turned on. And those would be, like, for instance, the nuclear power generators. They have very low operating costs. Higher price offers are then accepted until the total amount of generation offered equals the anticipated demand for electricity. The day-ahead price in each hour, usually these markets are hourly, is determined by the expected operating characteristics of the last generating unit that is scheduled to be dispatched. Okay. So if the last generating unit will only produce power if the price is $100 a megawatt hour, then everybody who's dispatched gets 100. Okay. And so the day-ahead price relative to the price of the fuels used to generate the electricity therefore reflects expected operating conditions. So the prices have information. And what we're trying to do in this study is tap into that information. Any questions? You're so polite. And we can see that in this scatter diagram for PJM. On the vertical axis is what I call the Sparks ratio. This is the ratio of the day-ahead price of electricity for each hour relative to the price of natural gas. Natural gas being an important fuel used to produce electricity. And you can see here, with the exception of these guys, that there's a clear relationship between the Sparks ratio. Now remember, this Sparks ratio is a day-ahead ratio. Okay? It's day ahead. The electricity load, this is what actually happens. And so if you know that the Sparks ratio is going to be, let's say, 60, you know you're not going to be here. You're going to be way over here. Okay? Okay, structure of the power industry. Here we have the generating stations. They produce the power. And this right here is a step-up transformer. Okay? The electricity is produced at low voltages and then is stepped up and then moved over the transmission system. It's stepped down again over here and then reaches final end-use consumers. Okay, so the point here is that electricity is produced at relatively low voltages, but is generally transported at high voltages so as to reduce losses. Okay. What's the economic value of electricity? Well, if you just look at the amount of money people spend on electricity, you get a number here of $370 billion for the last year that I have data. But that significantly understates the value of electricity. And to think of it, suppose the power in this room goes off. What would we do? We'd have to go to somewhere, we'd have to leave. We'd have to close this thing down. Almost everything we do involves, except sleeping, involves the use of electricity. Okay. This is really personal with me because I live in an area where we get all these outages and it makes me very unhappy. The economic contribution of this industry is much higher than this because electricity is critical to our modern lifestyles, and it gives rise to what economists call consumer surplus. For those of you who had econ, you are familiar with that term? Consumer surplus? Oh, good. The consumer surplus from electricity is quite huge. That's the consensus view of economists. So here's what we call, this is quantity of electricity, and here's the price of electricity. And this hypothetical curve here, this is a hypothetical demand curve. It's downward sloping. Does anyone remember, for those of you who took econ, why is the demand curve for a product downward sloping? downward sloping because as price goes up, people want to economize on the thing. A few years ago, the state of Maryland, in its wisdom, volunteered me for an energy conservation program whereby during the peak hours, I had to pay 25 cents per kilowatt hour. And so this would kick in at 8 p.m. Excuse me, it would kick off at 8 p.m. And at 8 p.m., it would go down to 3 cents. Guess when I turned the dishwasher on? 8:01. Okay. The point is that price matters. So the curve is downward sloping because people respond to prices. When price goes up, people, in general, will use less. But that's not my point. My point is the amount we spend is equal to price times quantity, which is, here's my price, P1. So the amount we spend is P times Q. P is this. The Q is that. And so the price times quantity is simply area A. But the amount of satisfaction that you receive from the electricity is everything under the curve, which would be A plus B. And so area B here is what economists call the consumer surplus. This is what you get above and beyond what you pay for. Yes?
Just to make sure I understand in Canada in general, the price for electricity is pretty much fixed.
In where?
Let's say Quebec or New Brunswick.
Okay, yes.
Right? It's pretty much fixed.
Yes.
So, I mean, that day-to-day forecast of the change of the electricity price is not really going to affect us. So is it different in the US? Do you guys have like day-to-day or like monthly change in the electricity cost for having that?
The short answer, you want the short answer or the long answer?
Well,
okay. The question is, and correct me if I'm misinterpreting, is that for most people, the price they pay is simply a fixed amount. And so how does that affect, how does this fit into this? Is that basically what you're saying? Okay. You're right. In most places, the price that you pay is a flat amount, with my exception being that case where I was volunteered to be in a special pilot project. As we'll see, the wholesale price of electricity can vary considerably. But the retail price, in most places, is flat. And this is actually a source of inefficiency to the system. Electricity is a commodity that almost always has the quote-unquote wrong price because the price doesn't change as market conditions change. Now we're moving into a new system. It's going to take a while. You've all heard of the smart grid. The smart grid offers potential to improve the performance of the electricity industry. But for it to achieve its potential, people need to get better price signals. So if the demand for power is really high, one way to get conservation is to have higher prices. Now, as an individual consumer, people don't like that. But it's one way to make the system work better. Does that answer your question? Okay. There's been a number of experiments for consumers with what's called real-time pricing. And those experiments tend to be very powerful results in the sense that they say that if people know what prices they're paying and they know what appliances are consuming all that electricity, that they will respond to prices. Part of the problem that we have is that if in your house you don't know what's sucking up all that electricity. And you don't get your bill until a month later, and so you're not in a position to really act in an optimal way. And so what the smart grid hopes to do is provide people with both information on their consumption and incentives that will induce more conservation. Yes?
How do you come to the conclusion that all of B is consumer surplus? Is that just definition? Because can't there be benefits that are less than B that you have?
In microeconomic theory, at one time consumer surplus was considered to be kind of controversial about 25 years ago. And a whole lot of economic theorists went in and they did the hard work. And what they found is that area B will be a very, very good approximation of the change in economic welfare. Now, there are cases where area B can deviate from the true change in welfare, and I can give you some, if you give me your card, I can send you the seminal article on that. It was from the American Economic Review. I believe it was in 1978. And the title of it was Consumer Surplus Without Apology. Okay. By Robert Willig. Okay. And this consensus about this consumer surplus, this is not something I just dreamed up. The wholesale price of electricity, wholesale, today it's about $35, $40, depending upon what part of the country you're in, and depending on what country you're in. So the wholesale price can be about $40 on average. But because of this consumer surplus notion, the value of lost load, this is the decline in economic welfare when there's a power outage, the value of lost load is around between $5,000 and $10,000 per megawatt hour. That's the consensus in the economic literature. So you have a commodity, it sells for $40, but if you don't have it, the loss in utility is many times that. And I can give you references on that if you want. Indicative of the high value of lost load, it's not unheard of for the real-time price of electricity in today's restructured electricity industry to be close to $1,000 per megawatt hour. This is from the New York Power System. They have, again, this day-ahead price of electricity. They have the real-time price of electricity. And you can see here, the blue is the day-ahead, and the black is the real time. And you can see here on January 21st, 2005, something went wrong. And the system operator went into what's called a reserve pickup. They didn't have enough power, so they had to take out their checkbook and write a check for, I think it's around $900 a megawatt hour. Now, we could focus just on the difference in the price and then multiply by the quantity to look at the economic impact. But I think that would miss something. I think what would be missed is the fact that this spike here represented a challenge to reliability of the entire system. The system didn't crash. In a way, the system worked. But the fact that the price had to rise so much was indicative that the power system conditions were not ideal. Okay, some stylized facts. The power grid is not a battery. Electricity, in general, cannot be stored in large quantities economically. System operators manage the variability in demand through forecasting. They forecast how much electricity people are going to want to know, going to want to consume. But what's interesting is that the error distributions in these forecasts have fat tails. Does anyone know what that means? It's not normal. It's not a Gaussian distribution. And what that means is that you have a lot of kurtosis in the error distribution, which means that there are days out there when the forecast is 1,000, 2,000, 3,000 megawatts off. And that's a problem. I did a calculation for the French power grid. Anyone here from France? Oh, good. I can talk about them. In a kurtosis for a normal distribution, anyone know? Yes. No. 3. 3. Although if you go to Excel and you calculate kurtosis using Excel, they do a comparative comparison, and so a normal distribution there would have a kurtosis of 0. Right. Okay. So it would have a 3. In the French, I had some time on my hands, and the French power grid, their kurtosis in their error distribution, the distribution of the forecast errors, was 23. Pardon me? The kurtosis, that fourth moment, you got your mean, standard deviation, skewness, kurtosis. Oh, man. And I don't want to pick on the French. If you look at the errors in the forecast, the load forecasting errors in the UK power grid, or the Irish power grid, or the Scandinavian power grids, the kurtosis is really high. It's an interesting point, but may have some interesting research potential here. Conventional generation is subject to occasional outages. Sometimes the equipment breaks down. And here's another interesting stylized facts. Most of the vast proportion of the power grid is an AC system, alternating current system. And what that means is that the flows on a transmission system follow the laws of physics, which you all know about. And what that means is that the power flows do not in general correspond to what's intended. So you may want your electricity to go from Ontario to New York, but it may not end up that way. It may go somewhere completely different. Okay. I've calculated the quote-unquote errors in the flows at some interfaces, and it's not unusual for the errors in the flows, the root mean squared errors, to be over 100%. Alternating current, because you're an alternating current system, there's a target level of frequency, desired level of voltage and current oscillations each second. In North America, we have a 60 hertz system, and most everywhere else, it's 50 hertz. In Japan, anyone here from Japan? They have both. Maintaining the desired level of frequency requires, if you want to have your 60 hertz or 50 hertz, electricity supply and demand have to be equal. That's a stringent requirement. System frequency falls when demand exceeds supply and rises when demand is less than supply. In either case, the reliability of the system is challenged, depending upon the deviation. System operators offset these electricity imbalances by dispatching what's called balancing power. And these deployments of balancing power, these are deployments to maintain frequency at its desired level, can be very large. And here we see this in the UK power grid. This is their deployments of balancing power. And if everything was just perfect, the balancing power deployments would be 0.
I mean, this is just a bunch of load that they're putting on the system in order to...
So it's generation either up or down to keep the system balanced. So in some of these cases, see that 1,000 there? They have to come up with 1,000 megawatt hours of power like that to keep the lights on. And in this case, right here, they had to tell some generator produce less by about 1,500 megawatts to keep the system balanced. And so this doesn't happen rarely, it happens all the time. Yes? For this system in the UK, the average power could be about 30,000. Okay, but the thing is, it's not, the averages aren't important because I would respectfully contend because they have to come up with these balancing up and balancing down, or else the system won't work at all. Question?
For when they tell them generators to go offline, they've already paid for that generation, so essentially they're losing money.
Oh yeah, there's yes, and in the UK, the customers are directly charged for these balancing events. Well, see what happens is that if you think you're going to need 1,000 megawatts, but you actually consume 2,000, and the system is short, okay, so let's suppose that you're short and the system is short. So you've only contracted for 1,000, but you actually used 2,000, and it turns out that the system is short, that's going to show up in your bill in a non-trivial way. Okay, so I talked about system frequency. Just here's some just raw data. Now, the idea for system frequency in the UK, and this is the target. This was not a good day. I'll be candid. Actually, today's a good day. If you go to the system, today's a nice, good day. This was not a good day. The red here is what they say are the limits. Yes?
Is this somewhere we can just search online?
If you send me an email, I'll send you the web link.
And it's just live?
Huh?
It's live?
They do it, they post the system frequency here every day. Now, in a better world, it's not the world we live in, they would freely give you an archive of what the system frequency is. And so what I do is I download this every day. Okay. What I'm doing is I'm doing a study that's looking at the system relationship between GICs and system frequency in the UK. Okay, so this was not a good day. You can see here they actually had too much electricity and they violated their own limits. But it gets better or worse because there's more to system stability than keeping the system frequency within the limits. There are actually, as we alluded to yesterday, there's actually two types of power: real power and reactive power. Real power keeps the lights on, but reactive power maintains the voltages required for system stability. And the sources of reactive power include generators and capacitors. Reactive power is consumed by transmission lines, transformers, and motors. Reactive power, excessive reactive power consumption, and David referred to this yesterday, has the potential to lead to voltage collapse and system instability. According to the United States Federal Energy Regulatory Commission, voltage collapse due to inadequate reactive power has been a contributing factor to a number of blackouts. The blackouts cited by FERC include a blackout on the West Coast back in '96, actually two of them, a blackout in '78 in France, blackout in Japan, a blackout in London, blackout in Sweden and Denmark, and one as well in Italy. They said reactive power deficiencies was a contributing cause of these blackouts. And FERC even notes that voltage collapse due to inadequate reactive power was a contributing factor to the blackout experienced by Hydro-Quebec on 13th March 1989. Moreover, the United States Canada Power System Outage Task Force investigated the causes of the blackout in the United States on August 14, 2003, and they said that reactive power problems were a contributing factor. This blackout in 2003, it originated in Ohio, one itsy-bitsy part of Ohio, and cascaded into an area that had a population of 50 million people. And the reason why it cascaded is because we have a power system now that's really, really integrated. And so if something goes wrong one place, it can affect other control areas. The lowest published estimate of the economic cost of this blackout was $4 billion. And here's an image from space. I thought you'd appreciate this. That's the blackout. Pardon me? This is North America. I don't have pictures of the other blackouts, but I'll put that on my list. Okay, section 2. That took a little longer than I thought. Section 2 here, but I think that was might be worth it. Now we want to talk about GICs and the PJM RTO. Okay. Now, if you're interested, there's a paper, as I mentioned, on the website, and so if you want to go and look at the details, most of it's there, and it also references some of the publications. This is what the PJM looked like during the sample period. Okay. And the important thing to note is that most of the load, most of the consumption's here in the east, but the generation's over here. The cheap generation's over here. And as a result, they're highly reliant on transmission through a 500 kV system. PJM operates both real-time and day-ahead markets. Prices are reported hourly. The prices are location-based, which means that the prices will be equal from here to there when there's no transmission constraints. But the prices can be really different when there's transmission issues. Here, this picture here, I mentioned that they have a real-time market and a day-ahead market. And what this picture looks at, I know it just looks like a bunch of stuff. This takes the real-time price and subtracts the day-ahead price for 2003. And you can see here, it's almost never zero. And my point is this, is that when this real-time price is much higher than the day-ahead price, this represents a challenge to the stability of the system. PJM has these what's called market hubs. The most two important hubs is they have one in the east and then one in the west. And these hubs are about 320 kilometers apart, and the prices of the two hubs are equal in the absence of transmission constraints. Now, PJM they move a lot of power around. Over the sample period, the average flows from the west to the east was about 5,000 megawatt hours each hour. That's more transfer capacity than between France and Germany. They make use of a 500 kV system. And what this graph shows is it shows the difference between prices in the east minus the prices in the west. And you can see here that most of the time they're positive, indicating that they do have these cases of transmission constraints, transmission issues. Okay, what St. Cyr and I did is we looked at these prices, and we thought we would do something really simple. Okay. Start off with something really simple. We organized our GIC data, our GIC proxy data, into 4 quartiles. The first quartile would be GIC 1, 2, 3, and 4. And then we looked at the positive differences in the prices, the real time minus the day ahead. And we organized them into 4 quartiles, something real simple. And then what we did is we looked at the observed frequencies for each of our cells. So we come up with a 4x4 table. And then what we do is we calculate expected frequencies under the null hypothesis of no relationship. And this is what we came up with. This is, here what we're looking at is we're looking here at the ratio of the observed to expected frequencies for the categories representing GICs and the 4th quartile of the real-time minus day ahead. So these 4th quartiles, these are the price spikes. Okay. And if everything was statistically independent, what should I get? I should get a ratio of 1. That the expected frequencies and the observed frequencies should be about the same. But is that what we get? No. You see here that in this first category, GIC1, this is with low geomagnetic activity, our observed relative to the frequency is less than 0.8. GIC4 is about 1.2. Based on the difference, we calculate a chi-square statistic. It's a non-parametric test statistic that makes no assumptions about the distribution. And it's also, one of the nice things about the chi-square, it has its shortcomings, but one of the nice things is that it's relatively immune to statistical fiddling. if you catch my drift. Question in the back. These are 25% of the sample, yes.
So that means that by that graph, the GICs influence the prices by on at least 75% of the time.
No, I wouldn't go that far. I wouldn't go that far. What I'm just looking at here is something just real simple. Is there a statistical relationship? And I'm not even looking at what the magnitude is. And I'm also more than willing to acknowledge all the other things that I'm not controlling here for those confounding things that you and I have talked about extensively. But this is just kind of a first pass. Now, what St. Cyr and I did in one of our studies is we used this methodology. We used it in PJM, and we used it also in, I think, 11 other power grids all around the world. And we found statistical support everywhere. But let's continue. So it's a non-parametric test statistic, which makes it ideal to say, is there a relationship? And so here's our chi-squared distribution. This blue here is our rejection region for the null hypothesis. The null hypothesis being there's no relationship. And so if our calculated chi-square statistics is to the right of this, then we reject the null hypothesis of no relationship. And the alpha here, that's our probability of a type 1 error. The calculated value of our test statistic was 85. The critical value was 26. And therefore, we reject the null hypothesis because we're way the heck over here. And we did this for other metrics, and we calculate what we call the p-value. And this p-value is the probability of observing this event under the assumption of the null hypothesis. So for instance, here we have the real-time congestion cost between the eastern and western hubs. And we come up with a p-value of 1.56 e to the minus 25, which is about the same probability of flipping a fair coin 40 times and coming up with heads every time. Now, I don't know about you, but if someone flipped a fair coin, quote unquote fair coin, 42 times, and it always comes up heads, I would probably surmise it's not a fair coin. Okay, so why are the prices affected? The bottom line here is that the GICs, what we believe is that the GICs impair the performance of the transformers. They move the power largely on a 500 kV system, and we have statistical evidence based on a multivariate analysis that the performance of these transformers is adversely affected. We also have published just a paper last month that points out that the GICs lead to adverse reactive power conditions. The transformers. PJM remotely monitors its 500 kV transformers for both internal temperature and the flow. Based on these readings, the transformers are constrained or unconstrained because they don't want the transformers to be damaged. So they constrain the flow when the temperatures are too high. And we did this GIC, this very simple test, again, and you get this. And you get a chi-square statistic where we reject the null hypothesis. And then what we did is we controlled for confounding effects. We put in our GIC proxy, expected hourly load, unexpected hourly load, proxies for known transmission constraints, planned imports and exports, and proxies for unobserved hour-of-the-day effects. And what we found for these transformers is that the estimation results indicate that increases in easy for me to say, increases in geomagnetic activity in excess of a threshold of 1.5 nanoteslas per minute increase the probability that one or more of the transformers will be constrained. Now, when I say constrained, they're not fried. They just simply limit the flow. But when the flow's limited, the prices are the prices change. The real-time prices change. We okay? Questions? Okay. So we did the chi-square. Then we do a multivariate to control for confounding effects. Our next stage of our research was to look at GICs and reactive power. It's well known that GICs can lead to excessive consumptions of reactive power. And there's a quote here by Kapperman basically saying that this is the principal challenge to reliability. Here's a nice figure from Molesky. He's showing here the GIC amps, and this is the reactive power consumption. And he's getting here a nice linear relationship between the GICs and the consumption. According to John Kapperman, the GICs increase reactive power consumption by a factor of approximately 8 over the course of about 6 minutes on the 13th of March, 1989. Minutes later, the high voltage lines needed to ensure electricity transfers to Montreal from James Bay, those lines tripped. And the amount of consumption, the amount of flows was around 8,000 megawatts. And when you're 8,000 megawatts short, it's no surprise that the system collapsed. Okay. Reactive power issues in PJM. The average transfers of electricity within PJM are large, but there are limits. And PJM monitors these limits to make sure that they don't violate the limits. Flows in excess of the limits violate their reactive power criteria. And they consider, and this is just not me, they consider adherence to the transfer limits at their internal interfaces within PJM to be critical to the reliability. So the point is they transfer the power from the west to the east. They have these large transfers, larger than the transfers between Germany and France. They monitor the system continuously, and what they'll do is they have these reactive power limits, and they think that these are one of the most critical reliability limits in their system. In their words, this is their words, reactive transfer limits are the most critical system reliability limits because they represent the largest potential system impact if exceeded. That's their words. Okay, more on reactive power. Generators in PJM are normally dispatched based on their costs. We talked about that first thing here. The lowest cost guys go first. Okay. One major exception to this is when there is bad reactive power conditions. When they have bad reactive power conditions, PJM goes through what's called a reactive off-cost operation. And what they do under a reactive off-cost operation is they redispatch their generators so as to not violate the reactive limits. Okay, so during a reactive off-cost operation, generators are redispatched in order to reduce power flows across the transmission lines that are vulnerable to voltage collapse. On average, at the eastern hub compared to the western hub, the average price is 70 cents per megawatt higher. But during a reactive off-cost event, on average, it's about $11 higher. Moreover, these reactive off-cost operations, in my opinion, indicate that the stability of the system is being challenged. What we did in our most recent paper is we modeled the status of the system as a binary variable. It had a value of 1 if a reactive off-cost event was declared, and is 0 otherwise. We used statistical controls for possible confounding factors with a focus on the inclusion of explanatory variables that reflected the expected operating conditions. We include ambient temperature, the actual load, and the actual consumption, the forecasted consumption, the intraday variability in the forecasted consumption, scheduled imports and exports with other control areas, the day-ahead prices relative to the prices of the fuels. We talked about that earlier, the spark spread. Relative fuel prices, and the intraday variability in the day-ahead prices. We use also proxies for known transmission constraints. We have binary variables for the hour of the day and the day of the week. In short, we threw in the kitchen sink. And we had our GIC proxy. This is based on the 1-minute geomagnetic data from the Fredericksburg Geomagnetic Observatory in Virginia. And what we estimated is what's called a Logit Model. This is our dependent variable. P here is the probability of the predicted probability of an off-cost operation. And so P over 1 minus P is what we call the odds ratio. And on the right-hand side, we have a constant term C. We have a parameter here in front of the GIC proxy, and then the X's are our control variables. One of the reasons why we use a Logit model is I presume here people are familiar with ordinary least squares. Ordinary least squares is a wonderful procedure, but if you use ordinary least squares when you have a binary event, you could actually come up with a negative predicted probability or a probability that's greater than 1. And that's not good. Results, we have highly statistically significant coefficients. For example, the coefficient on scheduled imports is positive and statistically significant. The reason why I think this is really important because it makes a lot of sense because when you have imports, the generation is occurring elsewhere. The generation leads to reactive power. The consumption consumes reactive power, so you're getting the consumption, but the production is taking place somewhere else. And so it stands to reason that the more reliant you are on imports from other areas, the higher the probability that you're going to have adverse reactive power conditions. With respect to the GIC proxy, the coefficient's positively and statistically significant, which is what we expect. The percent of in-sample correct predictions for on-cost status is 91%. The percent of correct predictions when the off-cost status is predicted is more modest, it's 70%. Here's 50 cases where I have predicted probabilities. Now you'll note here, in all these 50 cases, the predicted probability is pretty close to 1. Now I'm showing you this to make the point that this is not just about GICs. Because you see this thing here? For those of you in the front, you can probably see it. What's that? That's the GIC contribution. So in these 50 cases, the GIC contribution to the predicted probability is epsilon. Okay. So the model here was correctly predicting these events, but GICs were not were not a player. Over here, though, we get something different. Here, this is our GIC contribution, and the GIC contribution for this hour was about 60-something%. This was the dominant player in this reactive off-cost event, and obviously falls off to more modest levels. So the point is not that these GICs lead to these reactive off-cost events, but that they're a contributing factor. Can anything be done about this? Well, improved space weather forecasts would help a lot. But you all knew that. What you may not have realized is that modeling and forecasting the vulnerability of the system would probably also help. What this graph here shows is that the vulnerability of this power system to GICs in terms of reactive power conditions is not a constant. Based on the predicted outcomes, what we did is we calculated a vulnerability percentile in the absence of space weather. And so here's our 5th percentile. And so here is the probability of an off-cost event in the absence of space weather. And this is really low. Okay. And what the next column here is giving us the value of the GIC proxy that would increase the probability of the adverse reactive power event to 0.75. And what this indicates is that you would need a fairly robust storm, 342 nanoteslas per minute. This would be almost as severe as the Hydro-Quebec storm of '89. But this probability of an off-cost event in the absence of space weather is not a constant. My 95th percentile, the probability of this happening is about 33%. And the value of the GIC proxy needed to get you to the 75th percentile would be a more modest 98 nanoteslas per minute. Based on our results, we think that we can estimate these probabilities here, forecast them. Okay, conclusions. The research reported here supports the view that space weather had electricity market impacts during solar cycle 23, even though there's no published evidence of a major space-induced blackout during solar cycle 23. It had impacts, but no one noticed. The price impacts, I would contend, are like the canaries in the mine. They inform us that the reliability of the power system is being challenged. The good news is that it may not be insurmountable to forecast the terrestrial-based vulnerability of the power system, and that you probably want to do this even in the absence of any GIC threats. The forecast, however, would also position system operators to make better use of space weather forecasts. And here's some references. Thank you. Questions? I've obviously worn you all down. Yes?
Let's start with the practical side. Suppose that we are in a state that we can make forecasts. How long ahead of time would they need the forecast? How long does it take them to dispatch and bring online the additional generating capacity?
20 minutes. Now, that would not be ideal, but, and this isn't just me saying this. Frank Koza was asked that same question at the NRC workshop a few years ago. And if you can give them a forecast 20 minutes ahead of time, they'd be happy if it was good.
So they can bring up a power generator in a matter of, well, someone has to decide. That takes time.
Yes?
You have to give them a call or send an email, and then they have to start running that generator. That can be done in 20 minutes?
Absolutely. Not a coal facility. Those things are dogs. But if you had a combined cycle gas turbine, it's like flicking a switch. And if it's a single cycle gas turbine, it's even faster than that.
Well, so there's hope. The second question, why would we do it? Because what you're describing, I think, I'm just being a little facetious, cynical, or whatever here, or maybe just European, as in not in the midst.
And what power system did you grow up in? I may have data. Okay. Oh, the Democrat?
I think what you've been describing is a system in which the consumer pays a substantially higher price than the cost of production. So the loss of revenue to the power generator, the utility companies, the fluctuations on that driven by these phenomena is really quite small and doesn't really impact our price by very much. If we reduce the vulnerability to the utilities by that amount, would we notice it in the price that we pay substantially?
Probably not so much in the price, which is one of the reasons why I'm saying it's not really, it's not the money in terms of the real time versus day ahead prices, because I pay for electricity maybe 10 cents a kilowatt hour. The generating cost is probably about 5 cents of that, and the rest is simply transmission and distribution. So the savings in those real-time versus day-ahead prices, it could add up to a lot of money, but in percentage-wise, relative to the $327 billion, it's not that much. Where the gains are, where the potential gains are, it is in the improvement in the reliability of the system. And as I tried to stress, when people lose power, that has a significant economic cost. And I can provide you with the references, $5,000, $10,000 per megawatt of lost load. And as you think about the economy, where we're headed, where we're all on laptops here, and everything we do except for sleeping involves electricity. If we lose power, that is not a good day.
So the end of your title, the real impact to society, happens just beyond the points where you've been doing your study, when it goes beyond just being challenged, but something really goes wrong.
Yeah, because I don't have the data on the blackouts, but the fact that you have these challenges is indicating that, at least to me, that there will be cases, perhaps in the future, if you don't do something, where the challenges will overwhelm the system. Does that make sense? Okay. And I'm thinking back for another paper that I'm writing, I'm looking at the dispatch of emergency generation in the Netherlands. And the same thing. They could have been, for all I know, just a very short distance from having a blackout during the 2003 Halloween storms. Yes?
Can you estimate, like, compared to the normal weather, or I mean, to the failing systems because of the normal weather? How much money is lost because of the space weather and because of the normal weather, or because of the human mistake altogether? If it's significant.
I think I would probably say I'm not that far along in the research. But what I am saying is that even if you control for terrestrial-based weather, we still see these impacts. And one of the ironies is the system operators, they know because of normal weather that they need to have lots of reserves during the summer. Lots of reserves during the winter, because those winter and summer, those are lots of electricity gets consumed during those periods. Where they let their guard down in terms of having backup power, reserve power, is during the shoulder months, otherwise known as the fall and the spring. What's the challenge? What's the problem? The fall and the spring is when the geomagnetic storms are most likely to happen.
So, maybe I'm a little bit confused, but I mean, the economic cost of power or something doesn't matter whether or not like that.
The economic cost, I'm sorry, I missed the first part.
Doesn't seem like it matters so much if it's created in a market power grid or not, right? Is the reason that you're focusing on these market ones and using basically the
Better data.
Price, yeah, basically.
Because I have prices as that yield those expected, the yield of proxy for the expected operating conditions. In the other grids, like in the southeast United States, those things are black boxes. That you don't know when there's emergency generation. You don't know anything about their operating conditions. But where we use markets, there's information about the prices, about the forecasted load, yada yada yada. Pardon?
Is there any correlation with the solar activity in general? Other than particular space weather events, in general, does the prices respond to the activity, solar activity?
Well, yeah, if you look at the chi-square, you can see, you'll see that, and actually one of the papers that I'm in the process of doing is taking it to the next step and actually explicitly modeling the price spikes. And looking and where price spike is the real-time price exceeding the day-ahead price by a certain margin. And there I see that the price spikes are being driven by a whole host of factors, to be candid, but GICs as well.
Just in extreme cases, if the electricity is going to be dictated by market prices.
If electricity is...
If the electricity prices are going to be dictated by those in the markets. data about when a big solar storm's going to come? Promoting crashes.
Actually, contraire. Because if we know that there, if let's say everyone believes what I said, which may or may not be true, but if we know that there's going to be this stress on the system, then all the generators are going to want to get in on the action to take advantage of the elevated demand or the adverse power system conditions, and you're going to see more bidding into the market. Not because they're altruistic. Heavens, no. Adam Smith told us that. But because they're trying to make a buck. But keep in mind, yes, you have markets, but it's the system operator who is ultimately deciding how much power gets dispatched. Okay, so I'm not just leaving it entirely up to the market. But again, what fascinates me about the market is that the market prices, they tell us, they give us information on what might happen. And then with the market, if you see a price spike, like I showed you in New York, Nick, what day was that price spike? Yeah, I do want to have a take-home homework. What you might want to do is you might want to go to Intermagnet and find out exactly what happened. I think it was the 21st. What happened on January 21st, 2005? And send your answer to Nick, because I'm going camping.
I'm almost positive it's 27.
Oh, well, okay, you have the data. Okay, great.
Geomagnetic activity by arrow? If it doesn't happen, how much will it cost?
On average, it's probably not that big a number. But again, the averages are not the important metric, I would respectfully contend. The important metric is making sure that the lights stay on. Because if we see that if the price goes to $1,000 or $900, that's telling us that the system is being challenged considerably. And the lights could have gone off on that day. Does that make sense? It's like the canaries and the proverbial coal mine. Yes?
With my question, I didn't really understand your answer, but I just wanted to...
I have trouble with my answers too.
No, I have trouble with economical words. I just want to say that I think that it's really, compared to some accidents like in Fukushima or something, it's incomparable.
Oh, absolutely. No argument at all. Oh, the question is, okay, I think I have a better appreciation for your question. How does this compare to the other challenges faced by the power system? You had this terrible accident in Japan. And I guess what you're saying is, on the grand scheme of things, this is probably not at the top of the list. I would answer yes and no. Yes, the probability of, if you have a meltdown of a generating plant, a nuclear generator, that is really a bad thing. No argument there. But I think what's unique is the fact that the power system is so unprepared for these events. They understand what happens if there's a major snowstorm. Okay. They understand what happens if there's a hurricane. They understand those are well understood challenges. The space weather challenge is less understood. And in that way, it's somewhat, it can be somewhat more of a challenge. Is that better? That bright kid in the back. Yes, I know.
It relates to your question that you have made an estimate of essentially the differences in price ahead in the day market prices, integrated over all things attributable in likelihood to ground-produced, humanity-induced currents. But you would compare that number to your total interval. Like, what is the total value over that same period for those numbers? Would that not give you a percentage of impact of space weather related price challenges compared to the total?
I did that, and I think the number I got was like $1 a megawatt hour, something like that.
Out of the 40.
I think then the prices were lower. It's ended up like 2 or 3%. Okay, so in my first paper, which was vigorously contested, don't get me started. I came up with a monetary number. I've since said, my focus since then has been less to come up with a number, but instead lay out a mechanism whereby the system operators can avoid the space weather impacts. So if you'll notice here, this chart here, it's gone. Okay, the one that you can't see. Oh. The problem with coming up with a number, I've learned the hard way, is that half the people won't believe what you say, even if you've done everything is perfectly. The other half will say, well, gee, that's a bad number, and they'll just shake their hands. What this tells me is that the vulnerability of the system is not a constant. It's not insurmountable to forecast this vulnerability. The vulnerability without space weather. And then combine this with the space weather forecasts to provide the system operators improved reliability. Does that answer your question? Because this, I'm pretty confident we can predict. This, I don't do. And I think most of you all would have a tough time doing it. Questions?